Welcome to Mountain Bike Physics, Impulse Momentum Theorem. If you're going to improve your skills as a mountain bike rider, inevitably you're going to find yourself lying on the side of the trail in a mess, looking up at the sky. Here Ryan has a hard time negotiating this turn in the trail. In his attempts to improve his skill set, he's pushed the limits of his ability and the limits maybe even of the conditions in which he's riding, and finds himself upside down on the trail. Let's talk about impulse. Impulse is the product of the force and the time over which that force acts on an object. The longer it takes for Ryan to come to a rest after hitting the ground, the lower the average force acting on our rider. Notice Ryan is wearing a helmet. Always a good idea to wear a helmet. It's not a suggestion. It should be mandatory. If you notice here on the left of your frame is where the collision is going to occur, but on the right of the frame is a big tree. We're going to reference that right now, and then we'll draw our attention to that and the problem to follow. Feel free to come back and view the video anytime during the problem. All right, here's our problem. Ryan fails to make the turn, takes a header on the trail. His mass is 65.0 kilograms, his velocity is 25.0 kilometers per hour, and the collision occurs. He stops moving 0.850 seconds after impact. What is the average force exerted on the ground, or by the ground, on Ryan? And what if Ryan had hit the tree on the other side of the trail, and the time change of velocity is 0.150 seconds? Here's our solution. I'm going to go ahead and use the impulse momentum theorem. Force times delta t is equal to delta momentum. Delta momentum obviously is our final momentum, which will be 0, minus our initial momentum, which can be defined as mass times velocity, initial velocity. First thing we need to do mathematically is convert our units, kilometers per hour, to meters per second, so all of our units are in workable units. And our answer for our initial velocity is 6.94 meters per second. I'm going to rearrange our equation now to solve for the force. 0 minus 65.0 kilograms times 6.94 meters per second divided by 0.850 seconds gives us a force of 531 newtons. If Ryan were to have hit the tree on the other side of the trail, his stopping time would be 0.150 seconds. Let's redo this problem now. Same exact problem, but now with a shorter time. So it's 0 minus 65.0 kilograms times 6.94 meters per second. This time divided by 0.150 seconds. And find now our force is 3.01 times 10 to the third newtons, significantly larger force. The longer that Ryan is in motion after his impact, the smaller the forces that are exerted on his body by the ground.